Hello and welcome to the Examining the 5G Air Interface webinar. My name is Philip Nugent, so I am one of the senior technical trainers here at Mpirical, and I've got you for an hour to sort of explore some of the key terminology and capability of 5G. Now, in order to do that, I'm going to just share my screen and we're going to go through a bit of a presentation as well as diving into a few specifics here and there as well. Now, I will point out that you will be able to ask questions. We'll save those questions to the end of the webinar. So this session's going to last about 50 minutes, and then we'll have a sort of 10-minute at the end webinar Q&A session. So we'll activate those at that time. Feel free to fire questions in, and I'll be going through those at the end of the session. So the idea is to look at 5G in 50 minutes, and there's a lot to cover, so I'm not going to spend too much time going into certain introductions of myself or anything. I'm just going to dive straight into some of the key topics that we're going to be looking at today. So we're going to start by introducing 5G releases, but more specifically going into things like the 5G frequency bands and ranges. We're going to be looking at massive MIMO and beamforming, diving into a little bit about the introduction of protocols, and I'll leave that till that point in time, and a little bit about the scheduling aspects of 5G, just as a high level. And then we finish off with a little bit of a day in the life of a 5G device. Again, some of the terminology linking into the registration, the mobility, and just generally how a device might work. Now, we can't go into every aspect and every feature of 5G because there's too many to focus in on. But what we can do is, again, focus on some of the key terminology, and using the Q&A session, you can then dive into more detail. So the first topic we're going to look at is frequency bands and ranges. Now, before I dive into the specific frequency bands and ranges, it's worth remembering that 5G is standardized by the 3GPP, the Third Generation Partnership Project, and as such, we have different 3GPP releases applicable to 5G. Now, it started with release 15 or version 15 of the specifications, and the idea is initially that was called 5G Phase 1. It focused on enhanced mobile broadband, so EMBB services there, and if you like, the full suite of 5G wasn't really seen until release 16, where we got things like the ultra reliable low latency communications and the massive machine type communication aspects associated with 5G was part of the release 16 standards. Now, there's lots of other features, capabilities that came in with release 15 and release 16, and beyond that. So we've already got standardization of a release 17. There are release 17 devices. Now, release 17, lots of features. We added various enhanced features to do with things like satellite-based communications, or NTN, non-terrestrial networks, as well as we go through all of these releases, we start looking at things like private networks. We start looking at aspects associated with things like connected smart cities, V2X, vehicle to everything, and the list goes on and on and on. So we can't get into every single feature of every single release. We're just saying, okay, we're going to provide an insight into the air interface. Now, we're just finishing release 18. I just wanted to mention that. The reason being is that's called 5G Advanced. So we have 5G, 5G Advanced, a bit like we had LTE and LTE Advanced. And there's going to potentially be a 5G Advanced Pro further on down the line. Now, I want to talk about frequency ranges and frequency bands. And the reason I've done the releases first is because with each new release, you can get new frequency ranges and new frequency band, configurations. So to start with, we're going to go into the term frequency ranges. So frequency ranges, in the world of 5G, they introduced something called frequency range 1, or FR1. Now, frequency range 1 covers, I would I usually group that as low band and mid band. So low band is up to about 1 GHz, and between 1 and, in this case, 7 GHz, just over, we call that the mid band. So low band and mid band. I'll come back to that terminology a little bit later. So we have ranges of frequency bands in FR1. And when we start looking at release 15, when it first came out, they identified frequency range 2 as well. But that was subsequently enhanced. So frequency range 2 got made bigger. And because of that, we have frequency range 2-1 and 2-2. And you can see that frequency range, FR2, starts at 24 gigahertz and goes up. And we've now got standards and specifications with some allocation of FR2-2 channels in there as well. Again, we'll mention a little bit about that later when we talk about bandwidth as a discussion. Now, why do we have these frequency ranges? Well, it's more to do with different conformance of the devices. So the device might support certain features in frequency range 1, but it might not support them in frequency range 2, for example, and vice versa. So, it's all about conformance and capabilities. So from a cell site, you will have one or more cells coming off that cell site. And if we think about a sectored base station like 4G, 5G can have different channels, different frequencies coming off that particular cell site, and it might be there for coverage. So this will be typically your low band extended range type services, where we're starting to identify low frequencies, 600 to 700 megahertz there. We've got mid-band frequencies where we think about having more bandwidth, more capacity. So they're again frequencies above 1 gigahertz, typically below 7 gigahertz. And I've given some examples. Now, different countries have different band allocations. So these are just typical examples. Now, in that mid-band, you might have lots of capacity, and typically we do. So you might find in some scenarios, and especially small cell scenarios, you might be putting on more and more channels to get more and more capacity, aggregating the bands effectively. With 5G, and a lot of people, when they describe 5G, think about high frequencies and beamforming, and that, if you like, concept does exist, but it doesn't have to be just that. Typically, 5G is a mix of low band, mid band, and high band above 24 gigahertz. These high band signals, and typically, I would call that ultra high capacity or ultra capacity cell sites. So usually we'll have a mixture of bands, and it depends again on the service provider, or if it's a private network, what frequencies they have access to. Now, as an example, I'm based in the UK, so I've just grabbed some of the frequency bands that we might see 5G operating on. And they have band numbers. So these band numbers relate to certain frequency bands, certain frequencies. And in the color scheme here, green is related to the 5G, and I've put the purple color there as predominantly 4G based technologies. But there is a process of what they call refarming, where you can refarm the technology. So what was 4G could become 5G, and what was 2G, 3G could become 5G as well. I've not put 2G and 3G on this list, just at this high level. So some bands are 100% one technology. Other bands, depending on, again, the service provider in that particular allocation, they may have decided to make it 4G and 5G, or it might be that certain bands have only one channel and it's a 5G channel, for example. So we do have a mix of frequency bands and bandwidths. Now, the key thing here is bandwidth, because bandwidth denotes capacity and throughput and peak data rates potentially. Well, I say peak data rates. Peak data rates are usually aggregation of bands, and we'll describe that a little bit later in one of the other slides. So when we start talking about having a channel, it'll have a certain bandwidth. Now, I'm going to just talk about that for the perspective of 5G. So I could have a service provider here with a channel, a certain frequency, That's called a ARFCN, excuse me, an absolute radio frequency channel number. The NR stands for new radio. So when you describe 4G, you say LTE. When you describe 5G, we use the term NR, new radio. And effectively, 5G can do everything that 4G can. So it can operate low frequencies, mid frequencies, different bandwidth options. It's very flexible. And therefore, it could, in theory, just over time, it'll just wipe out 4G. However, there's no point in doing that just yet because we still have a lot of handset penetration on 4G. So it's as devices on the ground get upgraded to 5G capable, we can have more 5G in our network. So different service providers will have different channels, different bandwidths with different center frequencies. And in the light green here, you might find an operator, a service provider might have allocation in multiple locations. But I did mention the word carrier aggregation. That's like bonding channels. So rather than just listening to one channel, you listen to 2 or 3 or 4 or 5 to aggregate the performance of the device. So that's a little bit about the bands. Now, if you were to go into a handset, and in this slide here, you can see I've got this is actually off a mobile, looking at a mobile operator, but you can see this device is locked on to a network. It's got a certain frequency. So as you can see, it's about 3.4 gigahertz. As you can see there, it's the ARCN that we mentioned, the absolute radio frequency channel number is identified. Now, in addition to that, I mentioned the bandwidth. So in this example, this is a 50 megahertz channel. So this is what you would see when you're looking at a 5G cell from a handset perspective. We then need to think about a bit more information about the cells, and we could talk about the signals, the levels, but we can also talk about the identification of the cells. And usually you'll hear the term PCI, physical cell ID, to identify a cell within a sort of a local vicinity. And in this example, it says PCI 75, and we've also got another cell, which is a neighbor cell potentially, which is PCI 76. So we'll come back to some of that aspect a little bit later, but it was just this idea that, yes, you're going to lock on to a particular frequency, just like your car radio. You listen to a radio station, you lock onto that frequency, and effectively, you'll then listen to the channel. Now, bandwidth is key. So when you're looking at frequency range 1, we support different what's called duplexing mechanisms. Duplexing mechanisms are uplink and downlink communication. And you'll hear the term FDD and TDD. They're the most two common terms. So frequency division duplex, as in 2 frequencies are used, or TDD, which is time division duplex, which typically means you're only using 1 frequency. So it's my turn, it's your turn, it's my turn, it's your turn, etc. Now, in frequency range 1, up to that 7.125 gigahertz frequency, there are flexible bandwidth options from, as you can see, 5 megahertz all the way up to 100 megahertz. Now, just because it can go to 100 as a service provider, you might only have a 50 megahertz channel, and that's all you can actually do. Frequency range 2, you'll find we do a lot more beamforming, and it's a high frequency, so we've got other twists to do there. And what it also gives you access to is higher bandwidths per channel. So a channel technically could go up to 400 megahertz. If we went into frequency 2-2, which is up, as you can see, up at the sort of 50, 60, 70 gigahertz, the specifications now have included bandwidth options there as well, and you can see one of the channels could technically have a channel bandwidth of 2 gigahertz, which compared to maybe a low frequency doing 5 or 10 megahertz, that's going to be a massive difference in the performance and the data rate. But remember, they have different use cases, different coverage footprints that we need to describe. So that's a little bit about frequencies, frequency ranges, frequency bands, and different options. Now, when you start looking at a channel, that channel will have a certain capability. Now, in 5G, in the downlink, we use a certain waveform, a certain technology effectively to send the information to our devices. Now, that waveform is called, or related to, something called OFDM, orthogonal frequency division multiplexing. Now, we haven't got time to go into that in this webinar, but the idea is that is the way that we sort of take our digital information and put it onto an RF radio frequency carrier. Now, there's a technique to do that, and we use that in the downlink, and we can use that in the uplink. And we typically see that used by your smartphones, your iPhones, your Samsungs, etc. Now, the problem with this technique is it's not that power efficient. And as such, especially for things like IoT devices, massive machine type communication devices, there's another waveform. So I just wanted to mention that there is some technical differences between potentially a downlink and an uplink, depending on the device, the configuration, and its requirements. Now, when you start talking about OFDM, yeah, and you can see there's OFDM or cyclic prefix OFDM in the downlink, and something called discrete Fourier transform spread OFDM in the uplink. We're not going into those in this session. The key thing there is they both have this word orthogonal frequency division multiplexing in there. So what we're saying is, if we had a channel and it has a center frequency, it has a certain bandwidth, let's say 100 megahertz, for example, we don't just have one block of data going across the air interface. We actually create subcarriers. Now, we've done this in 4G. We've done it in other technologies. So some of the enhancements to Wi-Fi have subcarriers in there. So we've got a lot of stuff going on in the subcarrier space. Now, when you start talking about these subcarriers, they're spaced by different distances. So you'll hear the term subcarrier spacing. And that subcarrier spacing in the world of 5G, we call that numerology. So we have different numerologies. So these numerologies are just simply the subcarrier spacing. And as an example, there's my 100 megahertz channel. We're going to talk about the subcarrier spacing, but before we do, we're going to introduce another term which is very key to, you'll hear it in 4G. In 5G, it's subtly different. It's called a PRB, a physical resource block, and that typically means 12 subcarriers. The same as 4G, in a way, is 12 subcarriers for a PRB, a physical resource block. 5G is the same. However, 5G is slightly different, and the reason is we've got numerology, so we could have a PRB with 12 subcarriers at 15 kilohertz, but we could also have a PRB with 12 subcarriers at 30 kilohertz, and the resource would be bigger. Now, you might say, I prefer to have the 30 kilohertz because it's bigger. Well, that's not the only sort of rules that we have to abide by. And what you'll find is, as you go to these bigger numerologies, as in bigger subcarrier spacings, it does change time as well. So the idea is the symbol durations and everything else changes. So, it's not just a case of resources in the frequency domain. We have to think about resources in the time domain. But the subcarrier spacing is typically 15, 30, or 60 if you're down in the sort of frequency range 1. But we can also, as we go into frequency range 2, you'll see figures like 120 kilohertz, 240, 480, 960, and beyond being used as we go all the way up to that sort of 60, 70 gigahertz frequencies. And we do need bigger subcarrier spacing as we go to the higher frequencies as part of the design. Now, a key aspect of 5G is the use of massive MIMO. Now, again, it is a bit of I suppose in a way, a bit of a marketing term to try and sort of emphasize it's massive, it's big, it's got lots of capabilities. But generally, massive MIMO is a lot to do with beamforming, about creating narrow beams to users which are more efficient. So rather than me send the data to sort of everybody in a cell, I can, bit like shining a torch, instead of having a wide beam torch, I can have a narrow beam torch, and therefore less people might see it because they're not in the beam effectively. So when you start looking at 4G, 5G base stations, I've just got an example here, and again, we're not going into the specifics of this particular example. I've just said, look, there is a cell site. You might find off that cell site there may or may not be any massive MIMO. Now, typically, massive MIMO is the use of multiple what they call antenna elements to create an array effectively that allows the beam to be created. Now, in the world of massive MIMO, some service providers will start talking about the number of sort of arrays and transmitters effectively, and usually call about when you talk about MIMO, you say multiple input, multiple outputs. That's what MIMO stands for, and therefore you talk about multiple transmit. In there, and multiple receive. So the input is the transmitter into the antenna, output is what you get out of the antenna, which is receive. So multiple input, multiple receive. And sometimes that's written as 8T8R, 8 transmit, 8R. Now, that's not very massive in there, by a number 8, but it's still, again, an improvement from how we started life with 4G. Now, I will point out 4G has the capability to include beamforming as well, so it's not uniquely 5G's capability. It's gone backward compatible into 4G as well. But generally, we could do these sort of 8T8R beamforming solutions. They're usually designed for lower frequencies where we're using a lower cost 2D beamforming. 2D beamforming, I mean, is typically beamforming left to right. So steering the beam left to right, or potentially having that sort of flexibility to steer. Not that you have to steer a beam. Not that you have to have lots of beamforming. You can actually have a cell which has one beam, just like a normal cell that you would find in a traditional 4G cell. We also have adaptive antenna systems. And these adaptive antenna systems typically have more elements in them, designed for typically higher frequencies. And you might hear the term 64T, 64R, or 120T, 120R. And these are usually linked into 3D beamforming. Yeah, they're a lot more intelligent. We're sending fiber RF signals to these adaptive antenna systems, and we're creating the beams based on how we've implemented it. And this is all about improving the overall performance as well as the throughput of the cell, because we're now using these narrow torch beams, as we call them, to get a better connection. Now, when you start talking about beams in 5G, there's different terminology. So some people, you'll hear them say, oh, it's a service beam, or it's a broadcast beam. And there are a few other twists as well. So generally, I've got a device on the screen coming onto our 4G base station. The 4G base station is called a G node B, a new radio node B to be precise. And as it's going through the scanning process, so scanning the frequency bands, FR1, FR2, and the bands it supports, it's going to be looking for these beacons. Now, these beacons and some key information come on a regular basis as part of something called a SSB, a synchronization signal block. Now, in this example, you can see that I've got 8 of these sort of little squares occurring, and these are this relationship in this example at least is related to a number of SSB beams. Now, we don't transmit them all at the same time. So in this slide at the top there, you can see we've got time over here. So technically what we're going to say is the first one you're going to see is this beam over here, which is going to go across at this point here. So you can see that, the device might not hear that one because it's pointing in a different direction based on where the device is. And what's going to happen then is we do what's called a beam sweep. And that beam sweep involves us sending on beam 0, and these do have an index number. So 1, 2, 3, 4, 5, 6, 7 in this case. You can have one beam 0. You could have up to 4 beams or up to 8 beams. If you're doing high band, you can go all the way up to 64 broadcast beams. So in this case, I've only got the example of 8. And the idea is, in this example, my device probably can see beam 1 and 2 because it's in between those in my visualization. And it's going to use that information to access the cell, because it's going to read a bit of information. It'll indicate that, I can see there's beam sweep number 1, there's beam sweep number 2, and then it can start deciding how I access that particular cell. Now, as we go through the access procedure, what you'll find is the device will be told or be configured with resources. The device will respond back to the antenna, and as soon as you do that, potentially you know where the device is, you know where the signal's coming in from. But we can also use other techniques to do with allocation to create a more direct service beam. So service beams are typically a bit more tuned in to a user or a group of users. But in order to make sure we know where that beam should go, there's different capabilities that we can use to get that information to come back to the network. And you might hear in a 5G system, we have something called sounding reference signals. And these sounding reference signals, every period, usually every 20 milliseconds, let's say, the device can say reference, 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 the SRS, the sounding reference signals. And that signal being arrived on the antenna at the G node B, we can reciprocate that and go, oh, the device is there. Oh, no, it's now here. It's now here. And we can then use that to effectively either move the beam, steer the beam effectively, or switch the beam. Again, not all 5G has to be beam mobility. Okay, so the idea is there's different different permutations there. So we'll come back to some of that a little bit later. Again, as we're going through, just as I say, we'll do a Q&A session at the end there. You can start sort of throwing in certain questions. There is a sort of Q&A tab there that you'll be able to sort of start throwing in. And again, if you start filling those questions in, again, I will go through them at the end, and we'll just have a little bit of a wash up at the end of the session. So we've got two more sort of rough topics to talk about. I say an hour isn't a long time to dive into the specifics of 5G, but we are getting into some specifics already. But the idea is, I just want to talk a little bit about protocols. Okay, so what do I mean by protocols? Well, I'm actually going to go over into the learning management system that we have here in Mpirical to assist me to look at protocols. Now, I will point out at the end of this session, there's going to be a little feedback link and a little free sort of course offer that you can go and get. And as part of that, you'll also get access to this NetX application, which I'm going to look at now. So if you open up NetX within the learning management system, let me just do that very quickly. Obviously, we're going to be looking at 5G, so I'm going to click on the 5G Explore option here. It's going to load that up, and you can see NetX has loaded up there. And we're not looking at full 5G system engineering courses that like we run. We're just looking at a little webinar on the air interface, which is typically between this device and my G node B up here. Now, there's lots of other functions on this NetX application, but the interface is called the 5G UU interface in there, and that 5G UU interface is it's typically ISDN terminology. So UU's been used ever since 3G. The term UU's been used. So it's in 4G, 4G UU, 5G UU. But if you click on this is the good thing about NetX, we can go into the protocols. Yeah, and I can see I've got two sort of suites of protocols, and that aligns with this diagram here. On the left of the screen there, you can see at the top we've got some things like NAS, non-access stratum. These are control protocols. And then on the right, we've got the sort of user playing the IP side, for example. And this is what's on this NetX. So I can click on here, and you can see it's got the physical layer, and we have a suite of protocols: medium access control, radio link control, packet data convergence protocol. And the most important protocol for 5G has to be RRC, radio resource control. So that is the most important protocol. Understanding RRC is a key part of understanding the 5G air interface, because RRC, not only does it signal to and from the base station, it also configures the layers below and also encapsulates the layers above as well, which is NAS, non-access stratum. Now, the good thing about NetX here is if you go and click on any of these protocols, it will introduce those protocols, and it will give you a 3GPP link that you could click to go and download the specification. But that's obviously going into the more advanced requirements there. So you can see I've got a control plane, and I've also got a user plane, which is subtly different. So I've used NetX there, but generally, just as a quick intro to the protocols, you've got the physical layer. There are tens of specifications describing the physical layer. It's a complex topic. You can be there. We do a 5G air interface course. It's like 3 days, and part of that is just touching on the air interface. But it's a big topic. Notice the 5G specifications. Most of these here have the word 38. It's the 38 series from 3GPP. 36 was what we used in LTE. We've got the MAC layer. MAC layer is vital for scheduling. This schedules resources, multiplex information onto the physical layer. Radio link control. This is all about reliability. So what they call ARQ, automatic request repeat type scenario. So number 1, number 2, number 3. Did you get that? That's how we do it in RLC. Or we could go unacknowledged or transparent. PDCP. It does sequencing of information, but it's also where we would have all the security. So we've got a lot of integrity, encryption taking place at the PDCP layer when we need it. Going into the control plane, I've mentioned RRC, radio resource control. That's the signaling. We'll see a little bit of that later on, just before we finish off the session. And NAS is the higher layer procedures. NAS, non-access stratum, is all about talking to the core network. So access stratum is the talking to the base station. Non-access stratum is talking to the core network. And NAS could be signaling, but you can also do for IoT devices and text messaging. You could put user data like text messaging and non-IP data delivery over the NAS. So in theory, there is a little bit of user plane there as well. And then on the other side, that's the user plane. There's a protocol related to SDAP. So this is related to sort of service delivery aspects of the application. When I say the application, I'm talking about the delivery of a packet of data, and that packet might be IP. Typically it is. 5G supports Ethernet. That's very rare to see, but it's in the standards. Or it could be unstructured. Unstructured is usually more for some proprietary solutions or narrowband or LTM based solutions when they go on to 5G. Unstructured data is another option. So there's other flavors of information. Now, again, we're not going into any more detail than that as far as this session is concerned, but it just illustrates that there's a lot of protocols. Now, as part of doing this session, you'll get a little introduction offer to get access to NetX. We're also going to give you a little free access to an RRC protocols video course that you'll be able to go and have a look at. So that, again, you'll get that for free as well. So I strongly recommend you take us up on that and learn a little bit more about RRC. So the device, yes, we're talking about protocols, we're talking about resources. Typically, if you start thinking about a device will be registering on the network. When it registers on the network, we don't use the word attach. We use that word attach in 4G. The 5G terminology is to use the word register, or specifically registration is the term that we would typically use. Okay, sorry, my pointer's not working there. There it is. And then the idea is, if you think about a bit of a day in the life, we will talk about day in the life a little bit later. The device might be doing things like it might be sending data, video type procedures. It might be doing email. Somebody might be using it for some online gaming, etc. And the device will typically be in one of two states, typically between idle and connected. So this terminology is used in 4G as well. Now, there is another state in 5G called RRC inactive, but I'm going to come back to that a little bit later. Okay, so that is another thing to highlight. If you're a narrowband IoT or LTM device, that's been updated to incorporate connectivity to a 5G core if you want to. But those devices will be a lot less active than a smartphone. So when they do data, it'll be a smaller bit of smart metering information, for example. So their sort of cycle of connected idle is going to be different to a smartphone. Okay, so this is some of the states that you would hear when you're describing 5G, idle and connected. Now, when you are on a cell, you'll be looking at that cell, and I'm using a screenshot here from the Forsk Atoll 5G planning software there, and it's just trying to illustrate that I put a small cell on the side of a a junction here. And the color coding here is all about signal, the red being the strongest bit of the signal. Now, within the Forsk Atoll software, we use the term bearers. So those bearers relate to what they call modulation and coding schemes. We won't be going into that in any great detail, except to say that when it's red, it's more efficient and you can get more, either more users or more throughput through the system. If somebody is in sort of blue and green, what it means is the link's not very good. This is like when you see 1 bar, 2 bars on your phone. And what that means is it's not efficient, but it's also not very efficient for the cell either. So, those users typically drag the overall throughput of the cell down because they're not very efficient. But you can't tell everybody, oh, please all come and stand next to the base station. That would be quite a good app if it was ever created. Find your nearest base station. So we've talked about bandwidth. We've talked a little bit about doing data. And then the next question some people ask is like, what is the actual data rate of 5G? And that's a little bit of, that analogy of how long is a piece of string. It depends on how long the piece of string is. Same principle with data rate. It depends. Now, one of the key inputs to performance is bandwidth. So as you can see, for frequency range 1, we said it could go up to 100 megahertz in here. So let's just think of a scenario where you're just looking at one channel, a bit like in your car radio, listen to one radio channel. And what I'm saying here is it's one channel, and what we have is we've got either, when we're like in red, remember in the red in the previous diagram, we're close to the base station, the link's really good, which means we're using a high order modulation scheme. The modulation scheme is how you modulate the radio carrier with ones and zeros. And the bigger the number, 256 QAM, which is illustrated here. Yeah. Actually, I should say on this side, 256 QAM. The bigger the number, that's when you read on the previous diagram we saw earlier, 5 bars on your phone. If you blue or green on the previous slide, it was very much not very good connections, in which case you'll be doing QPSK, quadrature phase shift keying. Again, we're not here to go into the specifics of how they work. We'll also have different layers being used. Layers related to MIMO is a good example, and you might have 1 layer, 2 layer. If you start looking at certain beamforming techniques, it's typically 1 or 2. If you are looking at sort of scenarios with massive MIMO, again, it's that value. If you start talking about sort of low frequencies, typically you can have more layers. You can go to 4 layers, 8 layers, for example. Overheads are just a figure I wanted to include because that's all the broadcast and saying, hi, welcome to the operator. And scaling factor at the bottom of that square is all about error protection. So 1 is you're hugging the base station. I advise you not to all hug base stations, but if you were hugging a base station, your link's really good. But if you're at the edge of the cell with 1 bar, your link is not very good. You need lots of error protection, and that'll be the 0.4, 0.3 type scenarios. So when you are hugging a base station, that's the analogy, you've got 5 bars on your system. The idea is the bandwidth there, you can see if I take a 20 megahertz channel, would give you this sort of peak rate of 218 megabits per second of the channel. Now, that could be given to one user, that one user who's got this link characteristic, or we might have to share it out between other users, depending on the loading of the cell. But you can see the big channel gives you technically over 1 gigabits per second just for one channel. And then you can actually use carrier aggregation to get even higher data rates. But I just wanted to put the caveat there that if you've only got 1 or 2 bars on your phone, the link's not very good. You're going to change the modulation. You're going to have more error protection. And you can see for that same scenario, yeah, but the device now being further away with lots more noise, interference, etc. The idea is the performance is nowhere near as good. So 5G, don't assume that you're always going to get really high data rates. It depends on how it's being deployed, the bandwidth, and a few other aspects. So I've just done the same thing there for frequency range 2, just to say, okay, frequency range 2, it can go up to 400 megahertz, and it's almost a simple 4 times multiplier on there for one channel. Okay. So just for the last bit of the session, I'd say an hour goes really quick. I just wanted to talk a little bit about a day in the life of a handset. A couple of things to highlight here. So firstly, physical cell IDs is something that you'll find as part of any 5G deployment. A PCI value is a number between 0 and 507. We saw that on my screenshot of my device earlier. We'll see it again in a couple of slides' time. And that's going to have a certain number on different cells, and neighboring cells will also have a different value there. So the idea is, um, you'll plan this. Now, if you had like small cell 5G, which is all about more capacity, then those small cells all need PCIs, and you've got to just make sure that you plan your network. Now, typically a network would use a feature called SON, self-organizing networks. I will point out, yes, we are using a lot of AI in the RAN side of these networks now to statistically look at interference, the allocation, and reorder which PCI should be used in which cells to make it more efficient. So a day in the life of a device, you could spend a whole hour just talking about this first stage, by the way, but the idea is he's going to do a process of coming on, scanning the network, using your stored information, ultimately finding a cell site, looking at its PLMN, its public land mobile network. A cell site can support multiple PLMNs. And then once you've done that, you can read the system information messages and perform a cell selection to say, I want to camp on this particular cell. Once you've done that, we need to establish the connection to the cell site. That's called an RRC, Radio Resource Control Setup Procedure. That's coming up in the next slide. And then we can support the NAS procedures. And the NAS procedures is called the registration. So that's what we call switch on. A bit like the attach that we would use in a 4G system. So I've pulled a couple of things out there. So the first thing I've pulled out is the RRC setup procedure. So from a 5G device, you probe the network with something called a preamble code. Now, there's a lot of complexity of those codes. We're not going into them in this session, but you pick a number effectively, and you say, hi, 39. And I will point out, you also do that at a certain power level. So you don't just shout out really loud. You go, 39. And obviously the base station didn't hear you. So what you're going to do is you're going to shout out another number, 41, a bit louder. And then hopefully the base station hears you and says, right, whoever said 41, it's your turn. Have some resource. And you'll go, brilliant. And you'll set up your RRC connection by sending some RRC signaling. Now, this is covered off a little bit in some of the RRC course that we're giving away after this session. So you'll be able to go into RRC in more detail there. But you got the RRC setup request and the RRC setup message coming back. Now, it's a three-way handshake. So it's RRC setup request is the first message, and the setup is the second. These are part of something called a signaling radio bearer. So in 5G, we have SRBs, signaling radio bearers. And if we're doing any data, we call it DRBs, data radio bearers. And this is my three-way handshake that I mentioned there. So you've got this three-way RRC setup procedure. And it's this last message that typically includes some NAS messaging. And that NAS messaging is your registration, usually, as you're coming onto the system. Now, once you've got a connection to a cell site, you start having more signaling radio bearers, usually SRB1. And then when we get NAS and security, we go for SRB2. And there are others as well, which we're not going into in this session. Okay. So I've got 3 slides to go. I'm a little bit about 1 minute behind. So I'll just mention those very quickly. I talked about idle and connected earlier. There's also an inactive base state in RRC. That's new for 5G. Again, that'll be covered off in the RRC section to a certain degree. The idea being, when you start looking at the idle state, that's your phone on the desk, not connected, it does cell selection, reselection. Same as inactive. I'm not going to go to the specifics of inactive in this particular session. And then if you're connected to a cell site like 4G, you will be doing handovers. And you could be handing over to another NR, 5G cell, new radio, or to 4G, which is called EUTRA, the Evolved Universal Terrestrial Radio Access. So that mobility will depend if you're idle or connected. we had this diagram earlier with these different sort of sizes of cells, but what we can now appreciate is from the neighboring cells, there may be some overlap at the low band, but typically at the mid band, the high capacity layers, they typically overlap as well, because that's where you have a lot of users. But it depends again on your deployment and the size of the cells. So just to finish off, this is my last slide really, and it really just allows me to say that we can see now that serving cell that we've camped on and accessed effectively, and it's our primary cell, hence the little P next to the name. It's cell number 75, and it'll have a beam number that it's measuring. So that's the SSB, the synchronization signal block. So you could have 4 or up to 8, up to 64 beams. So on beam 2 of this particular site, and we've got some signal levels in there, and this is all going to assist us with the mobility. So we've got reference signal receive power, reference signal receive quality, and signal to interference noise ratios are in there, and they're used in idle to work out which cell to camp on, but also we report these back for the neighboring cells like the one below here, because that might be better for a handover process. So if that one starts getting stronger, we're going to report that and say, this one's stronger than you, can I please hand over? So that, if you like, concludes the session with respect to the slide deck I've got there. Before I dive into the sort of any questions, what I'm going to do here is I'm just going to switch over the streams in there. Hopefully that's switched over. You should be able to see a sort of an offer feedback coming through. If that's hopefully that's on the screen there. Someone can just confirm that's gone in terms of the process. So what whilst that's offer screens on the screen there, what I'm going to do is I'm going to just start going through a little bit of the questions that we've got, and obviously if we've got about 13 minutes here, so I will put that offer screen up on the end, at least at the end anyway, but for now I'm just going to stop sharing my screen. So there it is. So there's the offer screen that you can now see in terms of the process. So yeah, feel free to take that QR code. You're going to get a link for the feedback as well, and you'll receive an email to obviously to get access to the 5G protocols and the access to NetX, which I showed you a little bit about the protocols of the air interface. It does a lot more as well. There's a few videos in there to assist in terms of the process. So what I'm going to do now is I'm just going to start talking about the questions, and I might just bring up a whiteboard if I need to answer. So in no particular order, because again they're sort of on the system here. Is AI used for beaming at all? The answer is at present not really. You'll find usually that is a process that's in there in terms of the feedback and it's a mathematical process typically in the cell site, not a AI related aspect. AI is used a lot in the RAN, but you typically don't get it all for the beamforming side. Not that I've seen any. There may be a specific use case, but typically it's happening so quick in the adaptive antenna system, it doesn't typically go across. So that was that first question there in terms of the process. The next question I got, is beamforming used for control plane and user plane? Yes, it is. So you don't have to use beamforming. You could just have a one beam across the cell. That is allowed, especially in the low bands. So some vendors just like to have one beam in there, which is everything: control, user plane, the channel. When you talk about a service beam is the information to you. So your control plane and user plane. Now you might find, in addition to that service beam, you're also listening to the SSB, which is technically control. So you could actually have multiple beams multiple things going on that you have to listen to. So hopefully that answers that particular question there. The next one I've got on my list here, release 18 now supports aerial UEs. Um, uh, what you've, I suppose the key thing there is, as part of the deployments of 5G, there's lots of scenarios within the later releases. So yes, we've got likes of non-terrestrial networks, as in the base stations are in the sky, but as part of things like V2X, vehicle to everything, disaster recoveries. So the idea is your device is now a drone, for example, and you're getting 5G to the drone. Yes, the specifications have extra capabilities for that gone in there, and there's so many different twists to that as well. So again, just be looking into that. Which apps is used for 5G measurement? Um, I think you're going on about the example that I have on my screenshot. Again, there's different apps that you download. All I'll say is that I don't recommend any app as part of Empirical. Again, it depends on the use case, but you have various apps that are things like GNet Tracker, Cell Mapper, Network Signaling Guru are three to mention that, again, I commonly use just to have a look at the measurements of a cell. The data rate you talk about is practical or theory or theoretical. All I'll say there is when you start looking at data rates, if it was 256 QAM with the effective coding rate of 1, which was the figure that, like, for 100 megahertz was 1 gigabits per second, that is actually related to a practical data rate. But that practical data rate assumes that you've got one user in the cell who just so happens to be, 1 meter away from the antenna, and there's nobody else in the cell. So it's like 3 o'clock in the morning. There's no interference, and you've got all the capabilities. So there will always be a variance when it comes to practical rate on theoretical rate, based on the actual practical aspect of deploying cell sites. So yeah, you might find, well, I'm here, I've got 5 bars on my phone, it says 5G, I do a speed test, and I get 5 megabits per second if I'm looking, let's say, on a certain service provider. But what you don't know there is how many other people are on the network, watching YouTube, watching Instagram, and in terms of that process. Does the 5G straight frame structure is the same as 4G? Well, it's a 10 millisecond frame. It has subframes. The scheduling is totally different in a 5G system. Numerology is different. Reference signals are totally different. So the commonality is 10 millisecond and 1 millisecond subframes. That's the commonality. Everything else is fundamentally different at the physical layer. Next question on there. How do we measure the reference signal receive quality? Good question. The SSB, the synchronization signal block. And what I'll do is I'm just going to share my screen here. So just to put it into perspective, I had a frame earlier, and in that frame I showed this example of these SSBs being transmitted. And if you looked inside one of these SSBs, what you have inside there, and again, we're not going into too much detail here, but if I just draw a little example, what you have is, I'll do this as blue and this as green in this example. What you have is a primary synchronization sequence signal and a secondary, or SSS, secondary synchronization signal. And that's a known pattern that has a certain level. So technically, you've got your channel, which is, let's say, a 20 megahertz channel or 100 megahertz channel in there. And that's got a certain signal level, receive signal strength indicator. And then you've got your power of your SSS, which will go to a certain point, and that will give you, and if I just scroll over a little bit here, that'll give you your reference signal received power. Specifically, we usually put the word SS on the front of it because it's the secondary synchronization signal that we're talking about here. And the idea now is, because you've got that power level and you've got the RSSI level, you can now determine the reference signal received quality from that combination. So hopefully that gives you a good visualization in there. I'm going to just stop sharing my screen at that point. Okay, a couple more questions to go. What frequency band is used for private 5G in standalone? So standalone 5G, private 5G. The answer to that does depend a little bit on the country you're in. There's different regulation rules. You might be able to get some what they call shared access spectrum in a private 5G network. Some countries have rules that say that if that service provider covering the country hasn't got coverage in the area where you want your private 5G network, some regulators allow you to register the same frequency as the service providers, with certain caveats in there. So private 5G has the ability, as technically, to go over all of the same frequencies that a smartphone has. However, it will depend on your regulator and your deployment. The likes of Ofcom in the UK, for example, as a regulator, you're able to go to them and say, I would like a private 5G spectrum, and you'd then need to give them coordinates of where you're going to put the base stations, and the power levels and the frequencies are given to you. And the last one here, would a beamforming cell have a different specific identifier in a call data record? That's a good question, and the answer is no, it wouldn't. So the beam ID doesn't get put up to the CDRs, the call detail record level. So from a base station perspective, the G node B, as you're on a cell, all you're going to get is the new radio cell global identifier coming up from that G node B. But dynamically it could be changing beams, and the reason it doesn't do the beam thing is you could, for example, within a 1 minute call, go through like 50 beams, let's say, or hopping between them, and you just haven't got the scope for that level of recording in the billing record. So it's that hopefully answers that question there. I think I've gone through all of those. They're the questions I've got. I'm just going to quickly check if anybody's got any other questions there. I think I've answered all of those. I've just had a quick look at the chat, and thank you for putting them into the Q&A. Helped me there for everybody. So I've got about 2 more minutes, which is unlike me for doing a webinar. I'm usually about, if it's an hour webinar, I'm usually about an hour late in my delivery. But yeah, 2 minutes, I'll take that. Hopefully you've enjoyed the session. I've left the screen on there for a little bit of a feedback. Feel free to obviously take us up on that offer. You'll get access to the RRC protocols course, which is a bit niche, but again, just gives you an idea of what we do. You can also use that course because there will be ability to ask the trainer when you're in that course, which will typically be asking me. So you'll be able to come back to me and ask more questions through that avenue as well. Okay, so yeah, thank you again for joining in. Hope you enjoyed the session. The recording, etc., will be sent out early next week with how to get access to that.